Well, hello everybody. I hope you all hear me. I would like to have some response before I continue. At least one of you, please tell me if you hear me or not.
We can hear you.
Great. Okay, so today I have a pleasure to talk for your distinguished group. And I have selected to fill my slot with two basic pieces of information. One of them, not to take more than 5 minutes, would be to advertise my new course to be offered by ETF in spring 2021. And this is the course on creativity. The rest of the time will be devoted to a new paradigm, which you will see. I will tell you why I believe is extremely important these days. So, if you like to get to any course of mine, you get to my website. You just type Veljko Milutinovic into Google, or if you are lazy to type such a long name, you just put in Prof VM, Prof space VM, and then you get here and you click to teaching, and you have a bunch of bullets here, and the first one is on creativity. Now, my creativity course is organized around the block scheme that you see in the upper left corner of this screen, and includes 4 basic parts on methods, on the presentation approaches, on the management of creativity, and on examples. Why had I chosen this model to start with? Actually, there is a bunch of companies these days in California. Most of them are in California, but not all, that are putting a very interesting architecture onto a chip of 30 billion transistors. One of them is Esperanto, which, believe it or not, does have a research unit in Belgrade, mostly with people of ETF and math schools of the University of Belgrade. Well, what they doing is they're putting 4 Intel-like multi-cores plus 4,000 NVIDIA-like many cores. And this is about all that they are able to put onto a 30 billion transistor chip. Well, however, the next milestone on this exciting road is related to putting 100 billion transistors on a chip. And the question is what to put in that particular case. Or in other words, how to keep the remaining 70 billion transistors busy in the process. Well, since these machines are mostly oriented to machine learning in specific and artificial intelligence in general, appropriate accelerators are needed, or better to say, architectures that are extremely useful for this type of applications. Now, one of the architectural approach of interest is Systolic type, which is what Google TPU is using now. It takes about 1 billion transistors, not too many, because this is an ASIC technology in general. Everything is fixed, and such an architecture is able to do effectively only a small number of related algorithms, maybe 8 or 16. Typically those related to tensor calculus. You know, we have 10 basic tensor calculus operations on matrices, vectors, and data structures of the related type. So this is for sure a new citizen of this nation, and the rest, in the opinion of many, is best implemented by a reprogrammable accelerator that follows the DataFlow paradigm. This is a monster. You see here, it takes up to about 69 billion transistors to implement it. However, it can be made to be extremely effective and fast for all except the before mentioned 8 or 16 most frequent algorithms carved into the systolic array. The reality is, in a number of applications, this small number of algorithms carved into a systolic array occupy about 50% of the runtime, while the remaining zillion ones are responsible for the remaining 50% of the time. So the two structures, the systolic accelerator and the reprogrammer accelerator together cover about, well, up to 100 of the needed runtime. And in some cases, this reprogrammable accelerator is a conditio sine qua non, and that is why it is worth the effort putting or investing the remaining 69 billion transistors into something like this. Well, in my creativity course, I first cover the methods that could be used to enhance creativity, and this is theory. A paper of mine, a paper signed by 20 different professors of the School of Electrical Engineering in the Department of Computer Science and Engineering. Actually, all 20 who had a PhD at the time when the paper was published. Then a bunch of contributions coming from European universities, and of those in the USA, leaded with the MIT, which course was the raw model for this one to be created at ETF. Then, in the creativity presentation part, well, we give some advices on how to do presentations and how to do English language to be most effective in those presentations. And in the management part, I repeat basically a subset of the course that I took long ago at MIT in their business department, named Sloan School of Management and Business Administration. At the time when I decided to move back from United States to ETF in Belgrade, I had a bunch of money in my accounts at Purdue University, which I couldn't cash and get back home, nor could I buy something and bring it back home. Instead, the only thing I could do at that time was to invest that money into some knowledge gathering, which I did by paying for a small MBA at the MIT Sloan School of Management. And well, what I will be doing, I beg your pardon? Okay, just I have an interrupt coming from outside. What's the issue? People see me. They don't see me.
They see you, they don't see your slides.
Okay. Well, I'm now, I got the information that people are not seeing my slides. Okay, so I can, do you see them now? Right. Am I sharing the screen?
No, we don't see anything. We just see you.
Okay. So I put here, I click on share the contents, and then do you see? Do you?
Yes.
Now you do. Okay. I'm used to Zoom because all the teaching that I do for Indiana University and Purdue in the past semester was based on Zoom. So I'm now in the learning curve, and I apologize for that. Anyway, so just repeating, this is the structure that I was describing, and here you have the table explaining how much transistors each one of the structure elements takes. And this is about the course. First, the methods. My method, the RTI method, European and MIT, and then about the presentation parts, and then about the management part, where I repeat my experiences from the a small MBA at Sloan. And then I give a bunch of examples. And I try the examples to be state of the art, and all of them will be from the year 2020. So this is about the creativity course, and in each example, I explain what was the creativity method utilized to create the innovation. And then I tell you about the information, and then you have a programming example, which would correspond to a homework. So there will be 4 homework assignments. And this is all about the course. And now I'm switching to the DataFlow presentation, which one gets if you click here. Username is VM, and the password is student. And again, we are getting to the same basic introductory, because of all the elements in this future 100 billion transistor chip, you are basically well familiar with all the essential parts except for the DataFlow machinery. And this is now the slides here about the DataFlow course that I give each semester at the Indiana University in Bloomington, plus at another US university. When I go there, I like to visit 2 universities. So Indiana University is my kind of fix now, and the others are like variables. Red is the slides, PowerPoint that I showed. Blue are the stuff that one should read after my teaching session. And here I also have tools, because for all 4 homework assignments of my creativity course, there is lots of programming, and some of that is related to data flow, and the rest is related to other paradigms that we get into through one of the clouds around. Those who decide to enroll that course, which is eligible for all students of ETF, will see. Anyway, I will try today to run quickly to the first one. That one is a kind of anecdotic introduction into data flow. So, okay. It's now a bit slow, and so we have time for questions that may come from your side, if you have any. Any questions? I enjoy my teaching the most if I have many questions. So I will be very thankful to you if a question comes related to what I have just said, or to what you expect that I will be saying for the rest of my time today, which is another 30 minutes. Well, the time for questions is leaking out because most of my PowerPoint is almost being downloaded. Very well. Okay, so this PowerPoint presentation was generated by myself and 2 colleagues, one from Imperial in London and the other one from Stanford in Palo Alto, USA. So this is about ultimate data flow supercomputing for big data deep analytics. What I like to stress here is that this paradigm called data flow makes sense only for big data problems and only for problems that involve a huge amount of data reusability in their operation. Deep analytics in machine learning are kind of such an approach. Well, the data flow research started with the impact of the results generated by 4 different Nobel laureates. Richard Feynman got Nobel Prize in physics, and among other things, he wrote a book in which he claims that one can do logic and arithmetic with 0 energy lost, while moving the result to memory or I/O always does consume energy. From that one, it's easy to conclude that the best computing paradigm is the one which does not move data at all. And from the theory of graphs, it is known that the so-called execution graph structure is a structure characterized with this exact capability, being able to compute without moving data at all. I warmly suggest each one of you to find time to read this book of Richard Feynman called Lecture Notes in Computing. Now, Ilya Prigozhin got a Nobel Prize for chemistry, and I suggest everybody to read his famous book called Chaos. Well, in that one, he indicates. I beg your pardon?
Yeah, the same problem. Extremely problem.
Oh.
It's not on the PowerPoint, it's on the. You're still sharing the.
I'm now getting the information that once I switch to PowerPoint, I'm still sharing the Internet Explorer. Is that correct?
Yeah, we can see the browser on.
You cannot see the slides, right?
Yeah.
No slides.
Huh. Okay, let's see what. So it looks like when I switch to slides, the sharing disappeared. Do you have the sharing now?
Yeah, but we see the browser, not the slides.
Right, you see all your faces and names, right? Or you see the browser?
Browser.
Huh. Do you see your screen now?
We see you now. We see your camera view.
Names and initials as well, right?
Yeah.
Okay. So let me now to return to the PowerPoint. Okay. Now that I have maximized it, do you see my slide?
No.
Huh. When I maximize it, it disappears. Well, I don't know how is your experience with this particular platform, but the reason that the schools that I teach for in the States have chosen Zoom is because they told me the guy who now owns Zoom first was working for Skype, and then for Teams, and then for WebEx, and then he came to create Zoom by overcoming all shortcomings of his previous 3 babies. So do you see the slides now? Or not?
No, only yourself.
Okay, now you do see my slide, right?
Yeah.
If now I don't dare to maximize it because then I lose you again. Well, maybe we are now paying the price for my learning curve. So if you are able to follow this presentation from this, that should be okay. Right. Okay. So you remember Richard Feynman book title was computing lecture notes in computing. Dilya Prigozhin book Chaos tells that in any kind of system, including a computer system, if one injects energy into a system, one may, under specific conditions, decrease entropy. Then one gets more order in the system, and that creates more room for optimization. So in this particular case, the solution was found in separating temporal data and spatial data. Temporal data are like loop control variables, counter control variables, semaphores, and single scalars. And they should best be executed on the classical control flow machine, like Intel or NVIDIA, while the spatial data, like matrices, vectors, records or data structures of any complex type should best be executed at the novel paradigm, which is called DataFlow. Daniel Kahneman got the Nobel Prize in Economy, and I suggest everybody here to read his book called Thinking Fast, Thinking Slow. In that one, he advocates the wisdom of our grandfathers, saying that the morning is always more correct than the previous evening. He also, at one point, tells that the computing is like playing chess. From time to time, you have to sacrifice on something which is important, like tower or queen, in order to win on what is the most important, which is to win the game. And for that reason, we made the compiler flexible. So when calling the compiler, one can dial in the precision needed at different corners of an algorithm used. And finally, Tim Hunt, a Nobel Prize in Medicine, who shed light on the processes of creating, erasing, reproduction, and death of cells, has taught us that one is able at compile time to trade between latency and precision and get a better precision at no extra resources spent, only by adding more latency. Well, so the major axiom of computing is that whenever technology changes, you have to change the paradigm. Now we are past the FPGA era, moving to the era of the analog sea of gates, while as far as the applications, the big data problems are now past the exascale and moving into the brontoscale, which is 10 to the power of 27. So the question is, are the multi-cores like Intel or many cores like NVIDIA still the most effective ones? If the goal is to minimize the size and power and to maximize the speed and precision. Well, this was taken from the book of Feynman, where he tells that at the time when the von Neumann paradigm was invented, this ratio here of the time to compute something over the time to communicate the result to the next destination was diverging to infinity. And well, you get infinity when you divide by 0, meaning that at that time, communication times could have been neglected, since the wire was a lot slower than slow transistors and ray tubes before that. Consequently, the finite automata appears to be the best solution. And as you do know, when you execute a single machine instruction, you have up to 12 long-distance movements between the CPU and the place where data could be stored. Like you first fetch an instruction and you decode it, then you go for one data item and you bring it. And if the instruction was to add something, then you have to go for the second data item and bring it from somewhere. But for that, you may first have to synthesize the address. So you go for the first part of the address and back, and then for the second part of the address and back, and then you compute the address, and then you get the second operand, and you do the job, and then you place the result temporarily someplace else. So in this short story, you had 12 data movements across the medium. However, if the data movement costs you 0, then you don't care. You can have 12 or 12,000, you don't care. It is 12,000 times 0. However, Richard Feynman tells that as the time goes by, this t here means years or decades or centuries. That same ratio will start converging to 0. So the question is, where are we now? Why converging to 0? Because now we are dividing 0 with something which is not 0. Everything is relative here in computing. So the question is, where are we now? Closer to what was in 40s, in which case we should be extremely happy with our Intel or NVIDIA architecture, a lot closer to what I refer to as the Feynman's asymptote, in which case we have to think about a new paradigm, and data flow appears to be the optimal one to go. So I checked about the Intel, and this is what I got. They can do double precision floating point in only 10 picoseconds, but moving the data across the network may take up to 2000 picoseconds, meaning that these days one burns 200 times more energy to move the data to the next destination than to produce the data. And consequently, this is the execution graph of an algorithm, and the wisdom of the compiler is in creating a graph with the edges of the graph as short as absolutely possible. So when I compare control flow and data flow, I compare a slow wall clock and lightning. The slow wall clock, you remember, click, clack, 12 clicks and clacks for a single machine instruction to get executed. While here in lightning, what moves electrons is the voltage difference between input and output, and this is exactly the concept used by data flow machinery, because in data flow machinery it is the voltage difference between input and output that moves data to the data flow hardware. About programming. In von Neumann, we program our machines to microcontrol the movement of data, and in Feynman, we program to configure the hardware, and then the question is what moves the data? Well, it is external sources till the input of the data flow engine and voltage difference through the data flow engine. And well, so I think I will skip some of the slides, and I will show you a typical how a typical machinery looks. It can be used on the view or edge level to collect data from the Internet of Things and the wireless sensor networks. Then it can be used on the fog level as 1U boxes that do some pre-processing, and then on the cloud level we have 40U racks or trains of racks, where this is about the major successes of this approach. It can be used in finances, in geophysics, in science, and of course in engineering. This here is coming from JP Morgan. This slide is coming from JP Morgan. And if you look carefully into this one, you can see here that they claim, compared to the Intel CPU, a data flow engine brought to them a speed up of 1000x. And the data flow engine was a lot less expensive. The Citibank is using data flow for deep security, and if you go to the Chicago Mercantile Exchange, CME stands for Chicago Mercantile Exchange, which is the largest exchange for options and futures on the planet, you see that all the analytics they give to the traders was powered by Maxeller Technologies, which is one of the many companies that produce data flow engines these days. However, a company that I do homework assignments in my courses with. The New York NASDAQ is using it for trading, and now I'm switching to oil and gas. Look here, please. You know about Schlumberger. All oil companies know how to drill, but only very few of them, like Schlumberger or Schlumberger, depends on how you pronounce it, do know where to drill. Why? They own seismic vessels. They shoot a sonar gun down under, and waves bounce off the bottom of the ocean floor, or from the inner layers, or from the layers related to gas and oil. And all the bouncings get collected by a carpet, which is typically 2 miles by 1 mile, and then a processing has to be done. The question is the processing done on the boat? No way. Why? There is not enough power there. So all the data get put onto a disk, and the disk get put onto a helicopter, and the guy flies to the mainland, and there the data get processed by a supercomputer. However, once they decided to switch to DataFlow, which is not only high speed but also low power, the processing could become possible on the engine as well. Okay. Now, related to weather forecast, for this particular formula, which is related to shallow water weather forecast, it was shown that a data flow engine is 14 times faster than the here. At that time, the fastest machine on the planet, and it was also 9 times less power greedy, and at the same time 25 times more precise. Why more precise? Well, there is not enough time for that now, but if some people come to the course, you'll see. So Miloš Kotlar did his PhD thesis at ETF by showing how much one gets speed up and power savings from data flow compared to Intel and NVIDIA for the 10 algorithms related to TensorFlow. And this is like what the students all over the world, basically USA and Serbia, have done in the past few years through homework assignments or internships. And okay, so if you go to theappgallery.maxeller.com, you can see all kinds of everything from the coin miner to LZ decomposition and similar. The tools do exist at the Serbian Academy of Arts and Sciences that people use for homework and for research. And here you have a photo of the guy who was the inventor of the major aspects of this technology, and the picture was shot when these two visited the company in a year in which that company created the largest sales in ICT from Europe to the USA. The company is located in London. So due to the time constraints, I will now switch through some of the slides. And yeah, and like to show you, well, do you see the screen now? Because I have switched to full screen.
Yes, we see it, but it's not full screen. It's still minimized.
Okay. Anyway, you all know about the company JP Morgan. This is a $100 billion company, where a bigger one, which is called State Street and is located in Boston. And they are 27 trillion company dealing with portfolios of large banks and systems. They decided to build a large supercomputer to crank Bronto data in a place near Cork in Ireland. By the way, you know about Boolean algebra and Professor Boole, but you probably did not know that he was a professor at the University of Cork in Ireland when he invented his algebra. Anyway, the question is, how will this field look after a control flow machine is put there, which is able to crank 10 to the power of 27 data, which is Bronto data. Well, why? Because the monster has to be fed. So the data flow can exist on the software level and the analog levels. This is the typical speed ups and power reductions. Why is so much faster? Because we compile down to a lot lower level. You see? Do you see the screen now?
Yes.
Okay. So once again, you see the point. In control flow, which is NVIDIA or Intel, we program in order to microcontrol the movement of data, and here we program in order to carve canals. So when data comes to the input, it gets moved by the voltage difference between input and output in the ideal case, and that's the ultimate data flow, and you get the result a lot faster. At this point in time, when the analog sea of gates technology is not yet commercial, people implement data flow with FPGAs. So you have this ideal data movement driven by voltage differences only in between different stages of FPGAs, and that's why you have to compile down to the gate transfer level. And then while are the electricity bills so much smaller? Because this is the formula used by the utility companies to figure out how much you have to pay at the end of the month. And one issue here is the frequency, which is the most important one. And data flow engines work at frequencies about 200 times, about 20 times smaller. Also, these machines are about 20 times smaller because in Intel, data processing takes about 5% of the area, while here almost 100. And it's more precise, and this is the major successes. Now you have it on the Amazon, from where we take sophisticated software for all 4 homeworks of mine in this course on creativity. And this is where I generated all the slides for my entire coursework and for this particular presentation, which is a mountain where I grew up as a shepherd over summers to help breed goats and sheep at 2,000 meters above sea level. By the way, this is the Intel patent, and which explains how will the Intel DataFlow engine look like. And here we have an example from a project. Has shown huge advantages. And finally, here you see all the schools at which I delivered this same presentation as the one here. If you see the red color name, that means students were able to get a credit.
Excuse me, I don't think we see the right slide.
You cannot see the slide?
We see some slides, but I don't think it's the right slide.
Can you see a slide now?
Well, the same as before.
We can see the 61st slide with the factory.
And nothing after it. Okay, so it's either that I'm not enough familiar. Can you see the?
Yes.
Now you can. Well, I did nothing except clicking to move the slides. So either I'm, as you have already noticed, not familiar enough with this system, or this system is bugging on PowerPoint in some of the, I don't know which one. I usually like to blame myself rather than the other side. You will know it better than me. Anyway, this is the last slide. It is now 3:15. I was told to stop sharp at 3:15, and here you have the names of universities worldwide where I delivered this same lecture, either as a single lecture in their seminar, or as the first lecture in a course from which students were able to get credit for graduation, 1, 2, 3, or 6, depending on the schools, and these are in red. So thank you for your attention, and I'm now open for entertaining the questions that you may have.
I have one question. Is the data flow paradigm limited in terms of instructions, or is it provable that it's a Turing machine? Like for von Neumann architecture, we know that we can compute anything with it. Are there any limitations for data flow?
Excellent question. The data flow paradigm is also a general purpose engine, which sometimes is slower than control flow, like Intel or NVIDIA, and sometimes is faster, or a lot faster, or 1000x faster, as you had seen. Well, how fast this engine will be, or better to say, what will be the speed up that you get, depends on the contribution of loops to the overall execution time. So basically, this technology serves as an accelerator for loops. And I didn't have time to explain the details, which I do in my course, but basically, if you have a time-consuming loop in your Intel or NVIDIA code, then you take that loop out of your code, and you place its execution into the data flow accelerator, which is connected through a bus with the control flow host. So if you move a loop from the control flow host to the data flow accelerator, then inside the code of your control flow, you have to insert two operations, send the data to the accelerator, and then you maintain the integrity of your code. While on the other hand, the execution of that loop in the accelerator becomes a lot faster. So let's put it this way. Assume that the execution of the loop inside the accelerator takes 0 time in the first approximation. Then, if you had a piece of code that takes 100 time units to execute, and 99 of that was for loops, then once you move the loop out into the accelerator, the execution time of that code becomes 1. And you get a speed up of 100 over 1, which is 100. And obviously, in the case of JP Morgan, the loops were taking a lot more than 99.9% because once you migrate the loop, the execution time is not 0, but close to 0, and you also have the overhead time needed to move data to and from the accelerator. So if you have a high level of data reusability inside the accelerator, then the movement time to and from could be approximated with 0, and you get a huge speed up. Else, if you are just using the accelerator to multiply 2 numbers, then DataFlow engine will bring you a slow down compared to doing all that in a control flow host. So I hope my answer was clear enough, and I hope that now you have a good picture of the issue.
Yeah, it was good. Thanks.
Yeah. Also, what is important to say that I'm not advocating that the DataFlow engine, although capable of general purpose processing, should replace control flow, which is now used for general purpose processing. I'm just advocating that the two of them should work together. And if you go to archive, you will see an article co-authored by myself and Milan, who was so kind to host me today on his ETF student account, and a bunch of other people from California or Indiana, showing together the concept in which data flow and control flow are working together. Control flow represented with Intel-like and NVidia-like architectures, and control flow with Systolic and Reconfigurable. Any other question? Do you hear me? We have 7 more minutes, so maybe we better fill them up with questions rather than finish early.
We can hear you. Just there are not many questions usually at ETF.
Maybe I invent a question for you. How about that?
That could work.
Let's try. So, yeah. How many of you did read so far the book of Richard Feynman, Lecture Notes in Computing? None?
Seems 0.
Okay, that's a great book, and it is the chapter 5, which is crucial for the data flow research, where he tells 2 things. Number 1, logic and arithmetic could be done with 0 power, while moving the data always does consume power. How many of you read the book Think Slow from Kahneman, which now does exist in Serbian language as well? 0 again. this is a great one also. And maybe now instead of kind of burning your brains with details of data flow, I can give you an example from that book that would motivate you to read that book, which basically tells that on the when one has to decide something, the first thought is always wrong because one on the first hit you bases the decision on biases and prejudices, and then when one takes into consideration the math next morning, then one figures out a completely different answer, and the decision should be the opposite. So let me give you an example. Okay, assume you have two persons, Peter and John. Or Peter is a very precise in his work. He is very careful about the feelings of other people. He is frequently ill, like some trivial stuff, like flu or something, nothing special, and his body is very weak. So what do you think? What is his profession? A librarian or a tractor driver? You know, the tractor drivers are robust, macho guys, not very sensitive when it comes to the feelings of others and so on and so on. So what you think is the profession of the person I described? A librarian or a tractor driver? Well, obviously, you know that now I expect you to say a librarian. And if you have to bet, that would be a wrong bet to put your money on. Why? Because if you next morning call a specific part of math called statistics to help you, then you will see that in the United States, you have 40 tractor drivers against one librarian. And it is true that the great majority of tractor drivers are very robust, but it doesn't hold for all of them, maybe for 95% of them. And the 5% could be of the type that I just described. How much is 5% of 40? 2. And 2 is bigger than 1. So if you bet on a tractor driver, you have better chances to win than if you bet on a librarian. So this was a motivator for the book that I love. It has 40 sets of examples related to 40 different sub fields of math. And all examples are great, and you will enjoy it. Any other question for the last 2 minutes?
I remember hearing this example somewhere else, but haven't read the book. So someone copied it somewhere.
Yeah, this example actually was derived by Kahneman and another guy who died before the Nobel Prize was delivered. So only Kahneman got it.
Cool.
Well, any other question? Do you see me now? Do you still see me?
We see the slides and you.
Oh, great. So we have a great crescendo for the end. Well, if no more questions, no more technical questions, maybe somebody has a technical problem that he or she likes to share with the others. No? Maybe somebody has a private, personal problem that he or she likes to share with the others. No? Okay, this was supposed to be a small joke for the end. So thank you for coming. And I hope I see some of you in my course, which basically brings together all the experiences that I generated worldwide during the 70 years of my age. Meaning 12 years after PhD at ETF in Belgrade, 12 years of professorship at Purdue, which was top 5 when I came there for computer engineering, dropped to number 10, and recovered back to number 5 after I left it 12 years later to become a professor at ETF. And once I retired from ETF for 6 years now, I'm a professor at Indiana University. Now back at ETF as a visiting professor from the USA. Sometimes the fastest road to the neighboring building is through the USA. Thank you and enjoy the rest of the day. I wish you the rest of the day be fantastic.
Thank you.
Bye-bye.
Bye.